Ok. Hola a tothom. Avui inaugurem el cicle de conferències internacionals del MACA, que comencem a lo gran. Tenim l'honor de tenir amb nosaltres el James Tanton, que ens parlarà de com doblegar coses en 3 parts i altres estranyes fraccions. Avui, per sobretot, agrair la total disposició que va tenir el James per fer aquesta xerrada. A veure, crec que al James no li cal molta presentació, però si algú va una mica perdut, dir-vos que és un referent mundial de la divulgació matemàtica, cofundador del Global Math Project i inventor del fantàstic recurs educatiu Exploding Dots, que no podeu deixar de provar. Recordeu de, si us plau, mantenir els micros tancats i qualsevol pregunta o comentari que tingueu podeu fer servir al xat. Sense més, ara us deixo amb el James. Gràcies i que gaudiu. Hola a todos y todas. Hoy inauguramos hoy el ciclo de conferencias internacionales del MACA, que empieza a lo grande. Tenemos el honor de tener con nosotros a James Tanton, que nos hablará de cómo doblar cosas en 3 partes y otras extrañas fracciones. Quiero, por encima de todo, agradecer la disposición del James para hacer esta charla. Creo que al James no le hace falta mucha presentación, pero si a alguien va un poquito perdido, deciros que es un referente mundial de la divulgación matemática, cofundador de la Global Math Project, e inventor del fantástico recurso Exploding Dots, que no podéis dejar de probar, podéis buscar en la red. Recordad de mantener los micros cerrados, ¿vale? Y cualquier pregunta o comentario tenéis el chat que podéis utilizar. Sin más, os dejo con James. Gracias y que disfrutéis. Hello, everybody. Today we are opening the cycle of international conferences of MACA, starting in a big way. We are really pleased to have with us James Tanton, who will talk about how to fold things in thirds and other weird fractions. I want to thank James overall for his participation in this talk. I think James doesn't need much introduction, right? But if anyone is lost, I'd like to tell you that he's a world reference in math promotion, co-founder of the Global Math Project and inventor of the wonderful resource of Exploding Dots that you can miss checking. Remember, please, to keep the microphones muted, and any question or comment, you can use the chat. Without anything else, I leave you with James. James, thank you and enjoy.
Oh my goodness, my pleasure. Of those 3 languages, only one of those I could understand. So thank you very much for letting me speak in English tonight. But I will say, here's my attempt. Hola, buenas tardes. Did I get that kind of right? Tarde. Good to be here, everyone. What an absolute pleasure and what a joy to be with the museum. This is just wonderful. Thank you for organizing. This is going to be wonderful and blast. I'm going to have some fun. Hopefully you'll have some fun too. But we need these. If you haven't got one of these, a tie or a shoelace or a belt or a string or a floppy cucumber, quickly grab one now. So whilst people are running to get us something to fold, I will tell you my predicament. Here's a story that's not true. So the days before this weird, strange time that we're in, I would often go traveling on airplanes to visit fabulous people like yourselves and talk about mathematics. But I'd like to look professional, which means I like to wear one of these things, a tie. All right, so what I'm going to do is show you what happens. I often fly, and ideally I should hold my tie, pack my tie in my suitcase, but it's way too long to fit in my suitcase. So hopefully you can see my screen right now. If I'm not big on your screen, I'm not big on my screen, maybe enlarge me so you can see it. This is too long to fit in a suitcase. So I say, okay, well, I'll fold it. That makes sense. I'll fold it in half. Now, of course, that will fit in my suitcase, but here's my problem. I don't like checking my luggage. I will never check luggage if I can help it. I'll only carry hand luggage. So this is too long for my hand luggage. So I say, okay, I'll fold it again. Maybe fold it into quarters. That's fine. So I fold my tie into quarters, and that fits in my suitcase. That fits in my little hand luggage. But there's a problem. When you fold it, there's a crease mark there. So on a long flight of travel, it always gets bent down, and I get this terrible, embarrassing crease mark right there in the middle of my chest. It is embarrassing. I don't want a crease mark in the middle of my chest when I put my tie on. So I say to myself, what can I do? And I think and I think and I think, and I decide, if I could fold my tie into thirds, like something like this, that still fits in my suitcase, in my travel bag, that's good, and when I unpack my tie, that embarrassing crease mark will be at my knot. No one will see it. It's good. It's good. So I want thirds. But here's the trouble. I want to be a perfectionist. I want to see if I can get perfect thirds. If I can't get perfect thirds, I want to be so close to 1/3 that no one can tell the difference that I'm off. And I came up with this method. So what I have to do now, I'm going to have to stand up properly now. So I'm going to unplug my earphones. Can you still hear me this way? Can someone give me a thumbs up if you can hear me? Yes, okay, got a thumbs up, so you can hear me. So I came up with this method for folding something into thirds, and I want to see what you can think of it. It goes as follows. All right, let me get my camera so you can see me. So I'll start with my tie. I need to make my screen bigger so I can see myself, so I can see what I'm doing. There I am. You start with your tie, and you make a really bad guess. There is a really bad guess of 1/3. You see how bad that is? The whole thing doesn't fit in my screen. That's a bad guess of 1/3. So here's what I'm going to do to make this guess better. I'm going to hold where my guess is with one hand, and I'm going to pick up the very long end and fold it in half. All right. And then put my fingers in that loop and drop everything. All right, so now I've got another long end. I'm going to pick up the new long end, fold that in half, put my fingers in the loop, and drop everything. Whoop, shake it free. And now, if you look at that, that looks like it's better. It's like it's closer to being 1/3. That looks like a much better guess. So what I'm going to do is do it again. I'll do it again. Pick up the long end, fold it in half, put your fingers in the loop, drop. Pick up the new long end, fold it in half, put your fingers in the loop, and drop. And I think that's an even better guess of 1/3. In fact, I'll show it close on the screen. I think that is pretty good. You see a little bit off, so I'll do it again. Pick up the long end, fold it in half, drop. Pick up the new long end, fold it in half, drop. And I think that's a pretty good approximation to 1/3. But look at that. I think that is really, really quite close. Whoa, whoa. So our goal tonight is try to figure out what's going on there and why it works. So if you didn't catch that, okay, let me put my earphones back on so I can hear you guys properly. If you didn't catch that, let me do it with a piece of paper. So I'm now going to share my screen. Hopefully you can still hear me. Present my screen. I have to present my entire screen. It'll take me a moment to fuss here. All right, great. And hopefully you are now seeing my entire screen. Now, I can't see the chat window. I can't see any faces. If there's a problem, someone has to speak out loud and tell me you can't see. If you can see, we're good. No one said anything. I'm assuming everyone is seeing the screen. You should be seeing on the screen right now a piece of paper. So let me show you what I did again more slowly. Now you've got more of a view of what's going on. The idea was, take your strip of paper or your tie or your belt, whatever you're playing with, and make a really bad guess of 1/3. Bad guess. That's 1/3. Really bad. The trick was, take the long end, fold it in half, and find where that loop was. That's the crease mark would be there. Let me mark it so you can see it. Then you pick up the new long end, fold it in half, and hopefully you get a new spot that looks like a better version of 1/3. What do you think? Does that look better right there? Well, it does look better. But let me do it again. The trick was, pick up the long end, fold it in half, get a position. Bingo. Pick up the new long end, fold it in half, get a new position. And I claim that is a better position of 1/3. But I'll do it one more time. Long end, fold in half, long end, fold in half. Whoops. Try to do it properly. And, oh, you can't see it, but it looks like the crease mark is now right next to it. So the claim is that this one is a really close approximation to 1/3. So what I'm going to do is actually check it. I will fold it in that part there. I'll fold this other end, and let's look. Maybe I'm going to show it sideways on the camera. You see that? That looks pretty darn good. That is so close to 1/3. I'm actually truly impressed with myself. Whoa, whoa. So the question is, why does that work? What's going on? So let me see if I can explain the mathematics. I'm just give it away right now. I'm in the mood of sharing all my mathematics secrets right away. So here's the idea. Turns out the idea is surprisingly simple, though it took me weeks and weeks and months to think of the simple idea. It's this. Suppose I think I'm at some length L. Maybe it's 1/3, or maybe it's 2/3 for this side. But suppose I'm off by 2 centimeters. Suppose I have an error of 2 centimeters. Now think what happens when I fold it in half. I think that's length L. If I fold it in half, well, I will get now half the length. Now I'm going to think that this is half of L, but actually half of L plus 2 is half of L plus 1 centimeter. So my error was 2 centimeters, and it went down to an error of 1 centimeter. I thought I was at L with an error of 2 centimeters. Now I'm thinking about half of L, but now with half the error, 1 centimeter. In fact, in general, if I think I'm at position L, but there's some error, then every time I do a fold in half, I will think I'm at half of L. Whoops, can't see that, but I'll have half the error as well. So the point is, every time you do a fold, you make the error go down by a factor of 2. You get half the error. So let me stop sharing my screen because I want to show you this again. This is kind of cool. Oh, now you probably see me. Okay, now I'm back. All right, so that means what we just did. This is what we just did. You make a really bad guess on where you think 1/3 is. That's a really bad guess. So, whoop, you saw my tummy. Whoops. Bad guess of 1/3. So there's a bad guess of 1/3. This means this is a bad guess of 2/3. Let me fold the 2/3 in half. Now this should be 2/3 with half the error. Okay. Now, okay, so this is now, sorry, 1/3 and 2/3 with half the error. So I've folded the long piece in half again. I've now got what I think is 1/3 with half the error. That's a quarter of the error. But let me do it again. Now I think I'm at 1/3 and 2/3 with half the error. That's 1/8 the error. And let me do it again. So now I should be at 1/3 with half the error, with 1/16 the error that I had before. So I think that's probably so close that the human eye probably couldn't tell the difference. That looks very close to 1/3 to me. That looks pretty impressive. So it's got 1/16 the error I started with. Okay, so now I understand the maths. Now I'm going to reveal the true problem. I'm lying. The fraction 1/3 isn't best. I decided what's best for my chest and for my tie is not the fraction 1/3. I want the fraction, I'm writing it down so you can see it. I want the fraction 4/7. I want to fold my tie so that 4/7 is down the front of my chest. So now my challenge is to you, how could I fold my tie into the fraction 4/7 instead? What are we going to do for that one? So, I can't see your faces. Let's see if I can look at the gallery's view. There we go. I can see some of you now. Give it a try. Pick up your tie and make a bad guess of where 4/7 is. Just be bad. Here's my really bad guess of 4/7. That's an atrocious guess of 4/7. So now we have the challenge. We know every time we fold something in half, the error goes down by half. Now, which is easier to halve, the 4/7 or the 3/7? Now, I'm a mathematician, which means I don't like hard work. I will work very hard to not do hard work. So, I think halving 4/7 is much easier than halving 3/7. 4/7, half of that would make me go to 2/7. One fold. Okay, now I've got 2/7, which means I'm guessing the other side is what? 5/7? Is that right? I can't do arithmetic. Which one's easier to fold in half? 2/7 or 5/7? Well, 2/7. I could do that. Half of 2/7 would be 1/7. Uh-oh, what am I doing? I'm losing track of what I'm meant to be doing. But now I've got 1/7, and what's the other one going to have to be? 6/7? Yep, 6/7. Fold that one in half. That's easier, which now means I'm at 3/7. And, ooh, Now, if one side is 3/7, that means the other side is back to being 4/7, which is what I wanted. Now, how many folds is that? That was, I think, 1 fold, 2 folds, 3 folds. So we've done half of half of half the error. So this should be close to 4/7 with 1/8 the error that you started with. Does that actually look close to 4/7? Does your tie look close to 4/7? And if you didn't believe it, do it again. 4/7 and half. Gets me to what? 2/7 and 5/7. Do 5/7 and half. That gets me to 1/7 and 6/7. Do 6/7 and half. And that should get me to 3/7 and something really close to 4/7. Half of half of half of half of half of half of half. No, half. 6 halves. 6 halves the error. Okay, what's a half 6 times? Anyone type in the chat what the answer is? We have a chat here, don't we? What's half of a 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 half? I can't do arithmetic. All right, no one's able to chat. Doesn't matter. I think I just did it. Half of a half of a half of half of a half of a half is a 64th the error. Whoa. Okay, okay. But I've been lying again. It's not actually the fraction 1/3 that's good. It's not the fraction 4/7 that's good. When I really measured my chest and really measured my tie, I decided this fraction was the best fraction of all. I have to show it to you. Can't see myself. Hang on. 19/37. I decided that's the best fraction of all for my tie. Now you're on your own. Can you fold your tie or your belt or your shoelace, whatever you got, and give me a fraction so close to truly being 19/37? What would you have to do? Go for it. And I'm going to go make myself a cup of coffee, I'm going to make myself a snack, and I'll come back in about an hour.
Okay, tenim 5 minuts per provar. 5 minutes to come. Well, a couple of minutes.
No, I'll be here. I'll stay here. I promise to stay here, but give it a try. And I think I'm hearing what you're saying. Some people are saying in chat is that, yes, just make a bad guess. Start with a really bad guess. But then you have to ask yourself, what would I do with the bad guess? What will come next? So go for it. 1937. Where did that piece of paper go? There it is. And by the way, just so you know, I'm actually doing the work too. So I'm not being cruel. What I make you do, I'm doing as well. And I don't know if I'm having fun, but I'm doing it. And if you're very bored, just write in the chat, I am bored, I want this to stop. Give me the answer, and I'll give you the answer. If you're bored, let me know. I'm seeing some people are working on it. And yes, this really is a lovely limiting process. This is a good way to introduce students to limits, actually. We were getting limiting values to 1/3 and limiting values to 4/7. And now I'm asking for a limiting approach to fraction, horrible fraction, 19/37. I know. Some people are not getting anywhere. I know. Okay, maybe it is my turn. Let me give you my turn, because it feels like you're going to get lost in a sea of fractions. Is that what's happening right now? If I did try it, but my brain can't handle this very well. If you did try it, 19/37, no idea. 19/37, which means this one must be, what, 18/37? Can't do arithmetic. I can't do arithmetic. Which one's easier to fold in half? 19/37? No. 18/37 is easier. Let's fold that one in half. Gets me to 9/37. And what, 28/37? Okay, fold the 28 in half. 14/37. And 14 and 23/37. But the 14 is easier to fold in half. 7/37. 7 and 30/37. And then, 15/37. And you find yourself here for a very long time. Even now, I'm bored with my own question. So, okay, let me share my screen to you and show you what I did, because I didn't actually fold my tie. I found it tedious to fold my tie, and I couldn't keep track of things, so I started just writing it down on paper. Let me share my screen again. I have to fuss with the buttons, it'll be right there. And I'll show you my camera. All right, I actually did it. I wrote out all the fractions. So I started with 19/37, and I think you heard me say the other half had to be 18/37, and that was the one I ended up folding in half, which made it down to 9/37. And the other half would be 28/37, and fold the 28 in half gives me to 14/37. And I did it, and I started getting very nervous. I was wondering, will we ever go back to where we started? And I got nervous, and I was so relieved that eventually I did get back to 19/37. But it took forever. In fact, how many folds is that? Oh, actually, I haven't counted. Let me count the number of folds. It's one fold here, 2, 3, 4, 5. I ran a page, space, I had to go 5, then 6 folds this one. 7th, 8th, 9th, 10th, 11th fold up here. 12th, 13th, 14th, 15th, 16, 17, 18 folds. I had to fold my tie in half 18 times in order to get back to the fraction 19/37. Whoa, whoa. One would so lose track of doing this in practice if you just like trying to keep track of the numbers. But apparently, you can start with 19/37, a bad guess, do these 18 folds, and you'll be back to 19/37 with error half of 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 what you started with. The error goes down by a factor of a half 18 times. Let's see, am I stop sharing my screen? Maybe I'll stop sharing my screen. Okay, so we've just halved the error 18 times. Can someone with a calculator tell me what is half of a 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 half? What is 2 to the 18th power? Can someone tell me that? Because I don't know the number in my head. Can we do it in chat? How do I open up the chat window? What is 2 to the 18th power? Or what over 2 to the 18? What is 2 to the 18? What is 2 to the 18? Someone must have a calculator. But we're part of this 20%. Anyone have one of these things? Oh, someone did it. Excellent. So 2 to the 18 is 262144. It's 262,000, which means whatever error we started with, our error went down by a factor of 262,000. Whatever error we started with, it goes down by that factor. Okay, so if you really had the patience to go through all 18 folds, you'll have a tie that's so close to actually the 39/37th mark, no one with a human eye could tell the difference. This is amazing. I absolutely love it. Absolutely love it. But there's now a very deep mathematical question. I think We were lucky because we started with a fraction and we kept going, and we lucked out that we end up with the same fraction in the end. So our process stopped. Otherwise, we might be in an infinite loop. In fact, how do we know that if you don't just start with a fraction, you might end up going in a cycle, and you'll never get out of that cycle to ever get back to the fraction you want? Does this method always work, is my question. Does this method always work? If I start with a weird fraction, am I sure to get back to the beginning fraction? Or might I just end up being stuck in an infinite loop? Must this method always work? That is now a deep question. I wonder if anyone has any thoughts on that one. And actually, since we're less than 40 people, if you want to unmute yourself and if you have a comment, feel free to make a comment out loud. If you don't want to unmute yourself and want me to keep talking, I'm happy to keep talking in English with speed. Has something to do with the greatest common divisor? Probably does, actually. I'm sure that's my gut feeling as well. Well, actually, the greatest common divisor of what? That's a good question. Okay, I'm sorry my Spanish and Catalan aren't actually up to par. Hopefully people are saying both numbers, 19 and 37, or the 19 and the 18. What do we mean? Okay, I bet everyone's thinking something. You may have noticed something strange about the fractions I was choosing. I chose these fractions. 1/3, 4/7, 19/37. I always chose an odd denominator. What do you think of other fractions? Maybe fractions with an even denominator. For example, could you fold a tie into this, I'll be kind, into 3/4? Oh, and something more than that. I chose not just odd numbers, I chose prime numbers. Maybe I'm being sneaky by always choosing prime numbers. Oh, now you're onto me. Now you're onto me. Maybe Tanton is being sneaky, only choosing prime numbers for the bottoms of the fractions. All right, so what is going on? First of all, let's go back to this one. Could we do 3/4? Could we fold something into 3/4? And I think the answer is yes. To fold something into 3/4, what you could do is fold it in half, which you saw me do earlier on, and that will give me a crease mark at a half, and I could do that with accuracy. So there's a half, and now if I want to say 3/4 or even 1/4, both of them, I could do half of a half, gets me there, and the other half of a half means I've actually got all my quarters. I could do that. I could do 1/4, a half, and 3/4. So 3/4 is doable. What about 1/6? Could we fold something into 1/6 with our tools so far? What do you think? 1/6. Aha! Yes, yes. Joanne said exactly the right thing. We just did 1/3. The 1/3 was the first thing we did. So if we get to 1/3, like using the technique we did today, then all you have to do is halve it, and you'll get to 1/6. Okay, okay. So I think if anything's got an odd factor in it, we can get to it with our technique, and then just halve if we want to get to 1/6. Brilliant, brilliant. I like that. What about something awkward like 7/16? This one, 16th has no 3s in it, or 5s in it, or 7s in it. It's just nothing but 2s. 16 is like, could we do 7/16 on a piece of paper or a tie? What do you think? 7/8 and a half? Okay, go for 7/8. If you do 7/8, you can do 7/16. How do we get to 7/8 then? Oh, so doing 7/8, go for 1/8 on the other side, because on the other side will be 7/8. Okay, so how do you get to 1/8? You got it. You guys have so got it. Yes, exactly. I think we can get to all the quarters, all the 8ths, all the 16ths by doing this. Here's 1/2. Here's 1/4. Here's 1/8. Here's 1/16. Now I've got 1/16. I think I can get to all the 16ths. I could just keep folding my tie maybe like this. Do you see what I'm doing? I'm probably scrambling my fingers. I can just keep folding that 1/16 over and over and over again, and voila, there is my piece of paper folded into 16ths, which means I've now got all the 16th marks marked, which means I now know where 7/16 is and 3/16. Okay, I think we're good. It's all the even denominators we can now do. So now the question is odd numbers. And the question is, am I cheating by only choosing primes? Am I only choosing primes for a reason, or is that just coincidence? So what's an odd number that's not a prime? Maybe we should do a fraction like that. Someone give me an odd number that's not prime. Ninths, okay. Can we fold the tie into ninths? We'll try it. Try it with me. Let's make this interactive. I can't see you right now, but hopefully you do it. Step 1, make a bad guess. Bad guess. 1/9. 1/9? 8/9, is that right? Whoops, lost my earphone. All right, half of 8/9, I can halve that. Gets me to 4/9. So that should be 4/9 and 5/9. Half of 4/9, I can do that one. Gets me to 2/9. Half of 2/9 I can do. Gets me to 1/9. I'm back to 1/9. That was 3 folds, I think. 1 fold, 2 folds, 3 folds. That's 1/9 with 1/8 the error. So it worked with ninths, at least in that one example. So was James Tanton being sneaky with primes, or was it just a matter of working with all odd numbers? He could have done ninths. So I have a feeling 5/9 would also work. This is just mind-blowing, hurting my brain. My brain is hurting for so late in the evening in Catalonia and elsewhere in the world. All right, let's see. So how do we think this through? What was the question? I've even lost track of the question. The question was, how do you know when you play this game that you fold, 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 that you don't eventually just start repeating fractions and be forever stuck in a cycle and never get back to where you want? Now let me make the picture a little more clearer. How do I know this doesn't happen? I start some fraction, 8/nths, and I fold, 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 go on a path, go on a path, go on a path, go on a path, and maybe this will be terrible if I walked into a cycle and kept doing this loop forever and never got to my fraction again. Start with a fraction, go along for a while. This would be bad if I ever go into a cycle, because then I'll never get back to my fraction again. How do we explain whether this does or doesn't happen? Oh, my brain is hurting. My brain is hurting. If you want me to give it away, because I have thought about it, oh, like a third. Something like a third. Okay. Something like a third. Actually, give me a terrible fraction. Give me, someone write in the chat, a really horrible fraction with an odd denominator. And I'll work with it. Give me a fraction with a horrible fraction with an odd denominator. 6/17. 6/17. Okay, there it is, 6/17, which means the other half must be 11/17. All right. Now, if we go forward, we always halve the even side. I guess we'll halve 6/17 and make that 3/17 and 14/17. All right. And here's my question: could I go backwards? What fraction was up here to get me to 6/17 and 11/17? Can I see what? Could I go backwards? Go from here back up to there. From here back up to something else. Can we go backwards in this process? Oh, I've lost the chat. I can't see the chat. 12. Yes. Okay, you're on to me. Because you could see that, that 6/17 must have come from 12/17, and I guess the other side is 5/17. Yes, we can go backwards. All right, go backwards one more step, because I'm a little bit nervous about this one. Can this one go backwards? Can 12/17 and 2/17, can we go backwards from that? Some people saying no, and some people saying yes. Yes, you're right. The 12/17 can't be hard, because that gives me to 24/17. That's out of the range. But it could be that 2/17. That 2/17 could have 5/17, sorry. That 5/17 could have come from 10/17 and 7/17 on the other side. Yes, we could have gone backwards. So here's the thing. We've just discovered that this process can go forwards like we've been doing, but also go backwards, which is brilliant. That's brilliant, because that means this will never happen. We can always go forwards. That's what we've been doing all along. But now we've learned we can always go backwards. You can always undo what you did. Always go backwards. But here's the thing. If there was a little dangerous point like this, we'd be stuck going backwards. Going backwards can't take us on two different paths. Going backwards can only take us on one path, in which case there can't be a point like this where we get a split. That is, we can never fall into a cycle. The only way we can have this happen is we never go into a cycle. Whoop, and we just, whoops, that's bad. What am I doing? We never go into a cycle, and we can only ever eventually end up back where we started. There's only a finite number of fractions. We can't go into a cycle. We have to go through all the fractions we want. Wow. You have now, you've done it. You've now established it. There was nothing sneaky about my numbers. Oh my gosh, I've lost my, this is a messy page. I don't know why, I just happened to choose primes to begin with. That was just a coincidence. This will always work. You're right, this will work for any odd denominator, it will work. You'll always get every fraction you want, you'll never fall into a cycle. Also, you can get to the even ones by going to whichever odd one and then keep halving. This is brilliant. And then here's the question. This is actually very deep mathematics, and Esther actually asked the deep question. As far as I'm aware, no one knows on this planet right now how to predict how many steps it will take to go back. If I said to you, how many steps will it take me to go back to 1937? The only way I know how to answer that question right now is essentially to do it and say, 18. People are trying to characterize what makes this work the way it does. And people do not know how many steps, how to predict how many steps it will take to get back to the beginning fraction. This actually seems to be an open question right now. Now, there could be some maths out there that I've not stumbled upon in the literature, but I've been asking my high-powered number theory friends, what's going on? And they are stumped by it and do not know literature about this. So right now, in our little community, there are people right now talking about this very problem because people do not know how to predict the number of steps it will take. So this is just, I mean, what I love about this is just me playing with a tie and about the fraction 1/3. And we can do this with primary school kids, with elementary school kids. They have fun, actually. I mean, I had 5th graders last week just working out different fractions as they fold their ties, which is great because they're actually practicing their fraction arithmetic because they can better at it than I am. But that was fabulous. But at the same time, that very elementary activity of just practicing folding fractions leads to really deep, unsolved mathematics. No one knows how to predict the number of steps it will take to go back to the beginning fraction, which is amazing to me, absolutely amazing. All right, whoa. So to end off tonight, what I want to do now is do another experiment with you. Our brains are hurting, so I'm essentially stop all the hard work now, but let me ask this question instead. So for a tie, you could fold anywhere you like along a tie. A tie is like a whole continuous range of numbers, like every possible number appears in this continuum of a tie. You've got all the fractions here, you've got all the real numbers, you've got every type of number. But what about discrete chunks? What if I was playing with like lollies or candy or sweets or whatever you want to call it, whichever country you're in? These are actually chips from a Go board. Suppose I wanted to split a pile of chips like this, a tray of pebbles into fractions. So what I want to show you this can be very important for school kids because when you want to share candy, when you share lollies, when you want to share sweets, you've got to get your fractions right because kids want to count everything and want things to be shared equally. So I'm going to share my screen and give us another task. Oops, no, that's not showing my screen, it's the wrong button. Where's it gone? Share the screen button. Ooh, there it is. Entire screen. Sorry, this is not fun watching me fumble. Here I am. There's my camera. All right, all right. Here is all those pebbles. Let me get the camera in focus for you. There we go. All right, here's a bunch of pebbles. Let's go with an awkward fraction. Suppose I want to get 1/7 of the pebbles. I'm going to go for the fraction 1/7. All right, but I don't want to count them. So what I'm going to do is make a terrible guess. Here is a terrible guess of 1/7. All right, so what I'm going to do now is copy what we did for the tie. But I'm going to do it with piles instead. So I'm doing it with a tie, I'm going to do it with piles. So you take the big pile and split it in half. And I'm just going to eyeball it. I don't know where it is. I don't know, something like, yeah, that's good enough. Something like that. Split it in half and fold that big pile in half. And now make 2 piles like this. All right. So I thought that was 1/7 and 6/7. Now I think this is 3/7 and 4/7. Now let me split this one in half. Split this one in half. And I get something like, maybe one more, like that. I'm not counting. So now I think this is 2/7 and 5/7. Now I'm going to split this one in half. Okay, I'm not counting, honestly, I'm not counting. Now I think this is 6/7 and back to 1/7. All right, good enough, good enough. So as a check, I'm now going to actually count them. 2, 4, 6, 7. There are 7 pebbles here. 7. And now I'm going to count these ones. 2, 4, 6, 8, 10. Uno, duo, dos. No, uno, duo, tres. I can't do it. Sorry, I'm trying. 10. 2, 4, 6, 8, 10. That's 30. 2, 4, 6, 8, 10. 40. 2. I was going for the fraction 1/7. I kid you not, I wasn't cheating. I was not cheating. I actually just took the big pile, split it in half, took the new big pile, split it in half, and did it one more time, and I got to exactly 1/7. I lucked out. Oh my goodness. So at that point, I should stop sharing my screen, stop sharing. Am I back? Hopefully I'm back. I have to quit while I'm ahead. I was going to do another example of the pebbles, but I have to stop there because that was perfect. That was absolutely perfect. So I'm going to stop there and ask, okay, do you have any questions? Because 1/7 is actually 1/7 of 49. I have 49 pebbles in total. So I expect 1 pile of 7 and 1 pile of 42. Yep, 1/7 of 49, and I got it. It was right on the mark. And yes, my mind is blown too, because I did not expect that to work perfectly. So, do you have any questions for the remaining little part of tonight? And I'll answer them, or I'll do another experiment. If you want me to try to split this pile of pebbles into another fraction, I will try it. It's perfect for dividing spaghetti for your family. I agree. Yes. When family gets very fussed up about spaghetti, try this without counting spaghetti. Okay, so on that mark, for this 45-minute session, let me stop there. How about liquids? Oh, liquids, why not? I guess it'd be the same thing. It'd be like a tie. Instead of having like a 1/7 of a liter of water and 6/7 of a liter of water, or tie, you can actually just pour. Well, it's hard to do halves with jugs. If you could figure out how to do halves accurately with jugs, because we could fold accurately here, but you could eyeball it. I think it'd be okay. You'd be like, try it with liquids. It'd be like the tie, but you have to make a guess every time you halve it. But I was guessing with these pebbles, so it'd be like guessing with the pebbles. That sounds good. Liquids, great. All right, liquids, candy, and ties. Anything else we can share into fractions? This sounds great. All right, all. On that note, I think I'll hand it back over to my dear friends. There you go. Areas. Yes, why not? Okay, areas. I want 1/7 of this paper. How am I going to do that? I'm going to make a bad guess. There's a bad guess of 1/7. So what I'm going to do now to make it a better guess, I'll take the big area, which I think is 6/7, and split in half. Pretty good. I now think this is 3/7, and I now think these two make 4/7. Okay, I'll split this in half. 4/7 in half. I now think that's 2/7, which means I now think this pile here is 5/7. I'm now going to split the 2/7 in half. Here goes. Got these little pieces here. This I now think is 1/7 of the area of the original paper. I don't know, what do you think of that? Maybe we don't like having lots of little pieces of paper. But okay, it's the same idea. It's a lot of fun. A lot of fun. Okay, okay. Thanks everyone. I'll stop there. This is a blast. Keep thinking about it. But email me. I'm easy to find on the internet. If you've got some thoughts about how to predict how long it takes to get back to the original fraction, you'll be doing brand new original mathematics and it'll be fabulous. All right. Start thinking about that open problem. That'd be great. Let me know what you think. That'd be great. All right. Sergio, okay. Back to you.
Okay, thank you, James. Thank you to everybody. That's amazing and very engaging talk. Thank you very much. Well, I don't know if someone has any other question. You can unmute your microphones and ask. Si algú té alguna pregunta, podeu fer-la parlant, si voleu.
Yes. I think that for sure this sequence exists on the online internet, that database of sequences, you know?
Okay, hang on. Yeah.
Did you look for it in this database?
Oh, right, I've got the online integer sequence.
Yeah, that's right.
Online encyclopedia of integer sequences, yes.
Yes,
that's absolutely,
right.
Yes, of course, of course. Okay. And this is really related to the powers of 2, believe it or not, because we're always halving something. There's a question about when is 2 generating a cyclic group of the primes? And yes, it's not on there. It's not there, which is interesting. So it also further evidence that make me realize that people are still stuck on this. So yes, but you might find a version or some subclass that could be relevant on the encyclopedia of integer sequences. Yeah,
thanks.
It's not there as it stands.
Yeah, just a question. Maybe these numbers are related with the how to approximate any rational number with dyadic numbers. Okay, that's.
Yeah, it could be. Of course, that seems. I've not personally explored that route. I mean, there must be something to do with well, I mean, continued fraction expansions and all the rest of what are these approximating? What are we doing here? There's some depth in that way. Could be a good way to approach it. So yes, think about it. Let me know.
Okay, so we can finish here. So thank you very much to all the attendees.
Just one thing, I'm sorry. I was wondering if there is any kind of relation with the Egyptian method of multiply that is using the powers of 2.
That is, yes, as soon as you said that, I realized, oh my goodness, there should be a connection there of some kind. There's got to be some way to play that algorithm. Of course, I'm not actually representing sums of powers of 2 here per se, but of course, there's a nice binary connection obviously sitting here somewhere. I think really you could be onto something it's worth thinking about, and I've not thought about that, exploring that myself. So go for it. That's the answer to that one.
Okay.
Think about it and let us know. That's what I love about mathematics. Every question is an invitation for much more and much deeper thinking.
Yeah.
Doesn't matter what your background is, whatever level you're at, it's just perfect for you to think more. I love it.
Okay, so
sorry.
Sorry, Nestor.
No, it also reminded me the 3n+1 problem. Maybe there is some kind of connection. And if someone solves one, the other maybe it's closer. Yeah.
Good luck, sir. Good luck. Absolutely. No, there could be something deep lurking in here. It could be. I just haven't thought all the way through yet. Yeah. Love it.
Okay. So thank you very much. Remember that next week at the same place, the same time, with our next speaker is going to be David Martin. You cannot miss him. He's amazing also. And well, thank you again, James. That was amazing.
My pleasure.
Really.
My pleasure. Okay.
Moltes gràcies a tothom. Bona nit, moltes gràcies a tothom. Ens veiem la setmana que ve, recordeu, al mateix lloc, a la mateixa hora, amb el mateix link. Nos vemos la semana que viene con David Martin. No lo podéis perder, es increíble también. Y os enviaremos el link igual que esta vez. Muchísimas gracias a todos. Nada más, no tengo que decir nada más. Me he preparado la presentación, pero como veis, la cloenda no. Bueno, thank you.
We ain't goodbyes.
Okay. Bye, everyone. Real joy. Thank you, everyone. Thank you, Steve. Oh, thank you. All right. Have a good night, everyone. Bona nit.
Bona nit.
Thank you so much. Have a good night.
Adéu.
Thank you. Good night.
Thank you very much.
Right.